Swayam Prabha. Digital India. Educated India.
The first, that is introduction to aromatic acid. After that, effect of substituents on aromatic acid. So there are two kinds of an substituent, that will be electron withdrawing and electron donating substituents, and there is one more exception, that is ortho substituent. So we will see that what is that exception actually. After that, we will see method of preparation of an aromatic acid. After that, we will see reactions of an aromatic acid. After that, qualitative test of aromatic acids. Uses of aromatic acids. So these are the contents of the session. So let firstly see introduction to aromatic acid. So already you might be knowing what are the acids, aliphatic acids. So in case of an organic chemistry, there is only type of an acid. In case of an inorganic chemistry, you might have come across an HCl, H2SO4. So these are kind of an inorganic acid. So when it comes to an organic acid, so there is only a compound, or there is only a functional group said to be an acid, that is carboxylic acid. So carboxylic acids, they can be of two types. So one is aliphatic acid and second one is an aromatic acid. So now here we are dealing with an aromatic acids actually. So aromatic, why aromatic? Because it is having an aromatic ring attached to an carboxyl end. So at particular position it will have an carboxylic acid group, and due to which it is said to be an aromatic acid, and that carboxyl terminal, it is directly attached to an aromatic ring. So such kind of an compound is said to be an aromatic acid. So this is the structure of an benzoic acid, and we will see some more representative examples of an aromatic acid. So this one, it is salicylic acid. Medicinally it is quite important. After that, anthracite acid. So in many reactions it has been utilized as a precursor or in starting material. After that, phthalic acid. So it is also one of an pharmaceutically important compound. After that, orthotolic acid and M-nitrobenzoic acid. So ortho because it is at a ortho position, and M because nitro group, it is at a meta position. So these are some representative examples of an aromatic acids. So in all examples you can see that there are aromatic ring. So aromatic ring means an phenyl ring, and this phenyl ring, it is having one end of an carboxylic acid. So in all the compounds you can see that there is an carboxylic acid, and which is responsible for its acidity. So we will come across the concept what is that acidity, and it is having some substituent at particular positions, and that might be electron withdrawing, that might be electron donating substituents. Also on depending on that what kind of an acidity, whether the acidity increases or decreases. So we will be discussing that point also. So representative example in case of an aromatic acid, we will be looking that is benzoic acid. So benzoic acid is a colorless solid. Most oftenly students are using this benzoic acid for a practical purpose, because whenever you are coming across an practical qualitative determination of any compound, so first acid, most of the time the teacher gives you an benzoic acid to determine the end of a compound with all its property. Benzoic acid is slightly stronger than acetic acid. So what is the reason behind it? We seen in the last case or in the last session about that aliphatic amines are more stronger than an aromatic amines, but here case is different, that benzoic acid is slightly stronger than acetic acid. So we will come across why actually it happens, because this aliphatic acids compared to an benzoic acid, so benzoic acid, it is that oxygen atom, it is not directly attached with an aromatic ring, so there is no shifting of an electron from an carbon towards an benzene ring. So in the middle it will be having an carbon, and in front of that it is having an oxygen, so which plays an important role for to be an compound and acidic. And there is no resonance found in benzoic acid, so that is why resonance means what, that the charge is not been transferred from a carbon towards an aromatic ring, and that is why all the time electrons are present on an oxygen atom, so they will flow only into oxygens. So we will see that what is an carboxylate ion actually. After that, characteristics carbonyl IR stretching absorption of an benzoic acid, it is found at 1710 centimeter inverse. So it is for an 1710, it is for an carbonyl type of an functional group. So there are a lot many compounds which contains an carbonyl type of an functional group. So it may be aldehyde, it may be a ketone, it may be anhydrides. So there are a lot many amides, but higher absorption for a carbonyl, it is at 1710. And so to confirm it, So we have to look further over the spectra, that is 3400 centimeter inverse. When there is broad type of an absorption for an OH, so that compound is said to be an acid in the nature. Now coming towards an PMR spectra, or we can say H1 NMR. So PMR shows a singlet almost at delta value 10, and this singlet, it is of an carboxyl proton. The proton, whatever carboxyl end it is having, so that one singlet, it will be shown by that proton, and 7 delta values for aromatic proton. So remaining 5 protons with a singlet, if we are using an almost an 60 Hertz NMR, we will see an singlet. If we are using more frequency or more Hertz type of an NMR, so that will spread the signal, and this protons can be seen in the region of 7 delta values, that is aromatic proton, and 1 singlet. So from that it can be confirmed that it is an benzoic acid. So here we have taken only an representative example of an aromatic acid, that is an benzoic acid. So further reactions or further acidity, what we'll be talking, or further preparation methods, so that will be based on benzoic acid as a representative example of an aromatic acid. Now coming towards an acidity of an aromatic acids. So name itself indicates that compounds are acidic. But why they are acidic? Aromatic acids are acidic in nature due to its ability to donate a proton. It is as per Arrhenius theory that it will donate a proton. So compounds which are having an ability to donate a proton are said to be an acids, and which can accept a proton are said to be an bases. So whatever we seen in the last session of an amines, they can accept the protons, that is why they are said to be an basis. And after donating a proton, benzoic acid forms an carboxylate ion. So this is the structure of an benzoic acid, and reversible the carboxylate ion, it has been formed, and this carboxylate ion, it can have a resonance structure. So we will see what kind of a resonance structure it is having. When after losing an H plus cannot be effectively delocalized by aromatic ring. So from structure here you can see that, so one might be thinking that after donating an electron, or after donating a proton, so whatever the electrons are been remaining on an oxygen, so that will be shifted towards an molecular pi orbital of an aromatic ring, but it does not happen. And why it does not happen simply? Because the oxygen, it is not directly connected with an aromatic ring. So here in between it is having a carbon, and there is the charge cannot be shifted beyond this boundary, because here one of an carbon, it is electron rich, and here it is having a pi bond in the middle. And that is why, so whenever the resonance it has been forming, so ultimately again the again the electron rich oxygen, they will donate and towards an carbon, and it will form a pi bond, and as soon as it forms, this bond will break. So for this to happen means whenever there is shifting of an electron on an aromatic ring, for this to happen there should be no other oxygen atom, but here it is not possible. So here it is having an oxygen, and that is why, because as soon as one regains, one breaks, again one regains, again one breaks, again one regains, again one breaks. So that is why this resonance forms. They cannot give an electron towards an carbon or electron towards an aromatic ring, and there will be no resonance stabilization by an aromatic ring, or by having a substituted benzoic acid. So there will be no any kind of an resonance stabilization, and there is no delocalization of an charge or delocalization of an electrons in this aromatic ring, and they will intershift between these two carboxylate oxygens only. Some more explanation. This is because the oxygen of an carboxylate ions are not directly adjacent to an aromatic ring, and resonance structures cannot be drawn. So whatever that we were talking, this carboxylate anions, they are not directly attached to an oxygen. If it was that aromatic ring, it was been involved in delocalization of an pi electrons or the electrons over here. So there should be no carbon, and that will happen as it forms in phenol, that whatever the oxygen, when it is having a negative charge, so it delocalizes, but here in between it is having a carbon, and that is why there are only two these resonating structures, and not beyond this resonating structures it will form. Because the benzene ring does not participate in the resonance stabilization of an carboxylate group, substituent on the benzene ring influence the acidity primarily by inductive effect. Now one must know what is this inductive effect. So inductive effect, it is such kind of an effect, we can say, that it causes an polarity, and this polarity, see, like an example over here, you can see that carbon and oxygen, right? These are the two atoms, we can say, and this atom has an polarity. So atom has an polarity means what? The negative charge, it will be retained always by an oxygen, and a carbon, it will have an positive center, or it is electron deficient, and all the time oxygen will be an electron rich, and this happens due to difference in electronegativity. So whenever it comes to an inductive effect, so whatever the substituent present on an ring, so these substituents are attached with a single bond. So there cannot be a double bond. If it is double bond, this pi bond has to be broke, and there can be only a single bond, and this single bond it causes an polarity, and this polarity, it is due to a difference between the carbon on an aromatic ring and whatever the atom present in connection with that single bond. And this inductive effect, whether the groups are electron withdrawing or electron donating, so on that principle it works. So whatever the acidity, whether it will increase the acidity or decrease the acidity, it will depend on electron withdrawing substituents or electron donating substituent. So such kind of an effect, we can say that plus I effect or minus I effect, that is related with an inductive effect. And that so plus I effect and minus I effect means what kind of an charge it increases on an aromatic ring. So it defines. And inductive effect means simply an polarity between two atoms, and this polarity, it is within the sigma bond, or we can say an sigma electron. Whenever it comes to an pi bond or a certain other multiple bond, it becomes an mesomeric effect or electromeric effect. So here we are talking about only an inductive effect. So inductive effect will influence the acidity. So either it will be plus I or it donates an electron towards an aromatic ring. So these are electron releasing group, and it will donate an electron towards an aromatic ring, and that is why it destabilizes the aromatic ring, or we can say it destabilizes the charge on this oxygen, whatever the negative it has been formed after donating an proton. And methyl benzoic acid, it is less acidic than an benzoic acid. So benzoic acid is one of a representative example, and in the middle we have taken a benzoic acid. And what effect of a substituent does it have? Now here it is an methyl, so it is an electron releasing type of a substituent, and that is why it decreases the acidity. Also here you can see that there is one more group, that is oxygen. So oxygen, it is having a lone pair of an electron, and this lone pair of an electron, so there are two lone pair of an electron on oxygen, and whenever it has been attached, so it gives an electron towards an aromatic ring and destabilizes the ring, and which becomes an less acidic. And also in case of an amine, nitrogen, it is having a lone pair of an electron, and this lone pair of an electron, it will destabilize the ring, or it will reduce the acidity of an benzoic acid. because it is an electron donating, having a lone pair of an electron. And similarly, this CS3, it is not having a lone pair of an electron, but it has an ability to release an electron because it comes with category of an electron releasing substituent. We will see some acidity constants of substituted benzoic acid as well as an benzoic acid. So K, it is an acidity constant. Whenever acid dissociate, this concentration or the strength of an acid, it is determined by an K. So benzoic acid, it is having a value of an K that is 6.3 into 10 raised to minus 5. Now with some substituted benzoic acid having electron withdrawing substituents at para position, that is nitro, para-nitro benzoic acid, 36 into 10 raised to minus 5. Clearly it can be seen that due to electron withdrawing effect of a nitro group, the value has changed and value has increased of an K. So it is more strength or having more strength than a benzoic acid. After that, meta-nitro benzoic acid having value 32 into 10 raised to minus 5, and we will come to the numbers of para and meta. So we'll see some more examples. Again, an electron withdrawing having a value of 10.3 into 10 raised to minus 5, and it is again different for an para substituent. So it is 15.1 into 10 raised to minus 5. After that, for an electron releasing group, that is methyl, so it is 4.2 into 10 raised to minus 5, and for meta position it is 5.4 into 10 raised to minus 5. So interesting thing to see over here, there is effect of an position also on K values. So it does not matter that when it is at para position and when the substituent it is at meta position, the value does changes of an K. So it can be seen whenever it is an electron withdrawing effect, or it makes more strengthening than an benzoic acid. So in that case you can find that whenever substituent it is at para, values are quite more compared to an meta. So similarly in case of an chloride, for a value of an para, it is more than the value of an meta. So that effect, it might be due to stable para position, and also in case of an methyl, it is one of an electron releasing group and it creates an negative inductive effect. And here you can see the value that is 4.2 into 10 raised to minus 5, and for meta it is again different. So whenever it comes to an electron releasing group, for an meta acidity increases and for para acidity decreases, and whenever it comes to an electron withdrawing substituent, when it is at para, acidity increases, and when it comes to an meta, acidity decreases little bit. So not as compared to an benzoic acid, but little bit decreases compared to an para position of that substituent. And we will see what is an ortho effect. So ortho, these are different things that whenever we are having an ortho type of an substituent, so ortho type of an substituent, whether it is electron withdrawing or electron donating, so it increases the acidity. So what actually it happens, so we will see. Apart from this, there is one more exception, that is ortho substituent, and what that exception it is. Whether it is electron withdrawing or electron releasing group at an ortho position, all the time it will increase the acidity of an benzoic acid. Apart from this concept of an electron withdrawing or electron releasing, whenever it is an ortho substituent, so that electron releasing or electron withdrawing, it works only in case of when it is para substituted or when it is an meta substituted, but it does not work whenever it is an ortho substituent. So whenever it is having an ortho substituent, so acidity will increase of an benzoic acid, so whether it is electron withdrawing or electron releasing. The reason for this are not entirely known, although there may be some steric effect having substituent at ortho to one another. So such kind of an ortho, it has been substituted, and possible reason is that there may be some steric hindrances, or there may be some steric effect due to which acidity of an benzoic acid it increases, and it is due to that whatever the substituent present on the ortho site, so at number 2 position or at number 6 position, so this are having some steric effect with proton over here or oxygen over here, and that is why there may be increase in acidity, there may increase acidity of an benzoic acid. So it is not an entirely clear one, but it is just an proposed one what might be happening over there. Now we'll come towards an preparation of an aromatic acid. So here we will be discussing 5 methods of an preparation of an aromatic acids. So first method, that is oxidation of an alkyl benzene. Oxidation of an alkyl benzene with acidic potassium permanganate. It gives an benzoic acid. So one of a simple reaction that by only hitting toluene with an KMnO4, it forms an benzoic acid. So we can come across the end of reaction with whatever the permanganate color, it has been disappeared, and it introduces oxygen in between, and some remaining hydrogens, they come with this manganese. Whenever it has been added to a carbon dioxide, it forms an ester, and after ester it can be hydrolyzed or to form an benzoic acid. So this phenyl magnesium bromide, it is carried in a very dry conditions. So whatever ordinary flask we are utilizing for an reaction conditions, so that reaction flask or reaction condenser, it has been attached with some argon or some other kind of an gases which are not reactive in the nature, or sometimes guard tube like in calcium chloride or magnesium sulfate, it has been utilized, because whenever we are using this phenyl magnesium bromide, so it is quite sensitive to an water. So whenever it will come in a contact with an water, so automatically this reaction will be dissolved, or there will be a side product of an phenyl magnesium bromide, and such kind of an reagent, they are said to be an Grignard reagent. And CO2, it has been introduced in the between, and it happens likely because magnesium, it is, and Magnesium, it is and metal, and this metal will bear a positive charge, and whatever the compound is bromide or phenyl ring, it will have a negative charge on it. And whenever this positive center, it will have a negative center to it will get solubilized, and in water this sodium benzoic acid, it These reactions are very simple, so that there is no need of an heating. They can be done easily in the test tube also. So whenever it is been reacted with an NaOH, it forms an sodium benzoate, and whenever it is reacted with an sodium bicarbonate, it forms an sodium benzoate. Here indicative one thing is that it liberates an CO2. So liberation of an CO2, it indicates that compound it is acidic. We will come across this thing in case of a test for an benzoic acid. So in that case, whenever a compound it is acid, it will liberate an CO2. And formation of an sodium benzoate, it has been indicator. So this CO2, it remains as an indicator. A reaction as the reaction proceeds from benzoic acid to sodium benzoate. So CO2 will evolve, and as there is stoppage of an CO2 evolution, at that time all the benzoic acid it has been converted to an sodium benzoate, because we are using saturated solution of an sodium bicarbonate in excess with an benzoic acid, and it will form an sodium benzoate. So stoppage of an CO2 liberation, it indicates that whole of an sodium benzoate is formed from an benzoic acid. So this reaction we have seen in preparation of an aromatic acid also, but it was in reverse way. So it reacts with an alcohol in presence of an concentrated sulfuric acid as a catalyst to form an ester. So benzoic acid, it reacts with an alcohol, and H2SO4 acts as a catalyst over here, and it forms an ester, that is ethyl benzoate. So whenever we are reacting an benzoic acid with an alcohol, there is formation of a liquid. Benzoic acid, it is solid in nature, or white solid in the nature. Ethyl benzoate, it is liquid in the nature. So layer of an ethyl benzoate it is formed. So that can be an indicative. So proceeding of a reaction or end of a reaction. So one of a layer, it has been separated from in water, because H2SO4 it has been utilized, so it contains some amount of an water, and this layer of an ethyl benzoate it separates, or it forms an oily type of an compound, and from that it has been indicated that our benzoic acid it has been totally converted to an ethyl benzoate, because we are taking more moles compared to an benzoic acid of an alcohol and H2SO4 also. And later on it can be separated by a separating funnel. A layer of an ester and layer of an water containing an alcohol and H2SO4, that can be separated, and layer of an ester can be separated, because they are not soluble in water or alcohol, and all of the solid it has been converted to an. After that reaction of an aromatic acid, that is acyl halide formation. So there can be two ways to form an acyl halide. Benzoic acid, when reacts with an phosphorus pentachloride or thionyl chloride, it forms an benzoyl chloride. So there are two reagents. One is phosphorus pentachloride, and it forms an benzoyl chloride, giving away a side product POCl3 plus HCl. And when it reacts with an thionyl chloride, the same will be the end product, that is benzoyl chloride, liberating SO2 gas plus HCl. So here it is also been indicated with this SO2 gas. Reaction of an aromatic acid, next reaction, that is reduction to benzyl alcohol. Benzoic acid undergoes reduction with lithium aluminum hydride to give benzyl alcohol. Benzoic acid plus lithium aluminum hydride, and it gives an benzyl alcohol. If we come towards a mechanism of this reaction, this aluminum, it is metal in nature, and what lithium is also a metal in nature, but it is not so stronger as compared to an aluminum. So this aluminum, whenever it liberates an hydride ion, so hydride ion, it means H minus ion, and this H minus ion, it is having a negative charge, so H minus ion, so they will come towards an electron deficient carbon, because this carbon, it is an electron deficient, it is having an adjacent this oxygen atom, and as soon as the hydride ion, it approaches the carbon, which is electron deficient center, and it attaches because it is having a negative charge, and this carbon, it will have definitely a positive center partially because it is having an electronegative oxygen, and this pi bond, it will break, and one more hydride ion, it will be added, and there afterwards we can see that it forms an benzyl alcohol. Aromatic acid turns blue litmus paper red, as it is given by an aliphatic also, and this is due to aromatic acids are acid in nature. So whatever we have seen that it has a capability to donate a proton or to lose a proton, so they are acidic in the nature. So blue color litmus paper, when it is dipped in the solution of an acid, so it will turn red. And also apart from this, a pH paper, when pH paper, it is dipped into a solution of an acid, so it becomes red, or it will show pH less than 7, means above the, we can say from range 1 to 7, So 7, it is a neutral one, but that is not a recommended one. Litmus test, it is compounds which are soluble in the water will give a litmus test. Second test, that is a bicarbonate test. Saturated solution of an sodium bicarbonate when reacted with an aromatic acid liberates an carbon dioxide, forming a salt. Further addition of an HCl gives a precipitate of an acid. So this is at the first instant, the observer sees that carbon dioxide, it has been evolved. When it is only an acid, that time only carbon dioxide it has been evolved. So for any other compound, it does not give an carbon dioxide, and it is due to that we have seen in case of a reaction also. Sodium bicarbonate, it contains an carbonate group. So here you can see it. The sodium bicarbonate reacted with an benzoic acid, it forms an salt of an benzoic acid, or we can say an ester, sodium benzoate, and with that it liberates an carbon dioxide. So small bubbles of an carbon dioxide, they have been evolved in the test tube. And also there is one more observation, that benzoic acid, it is not fully soluble in water, and whenever it turns to an salt, it becomes soluble, and this solubility, it is due to an forming of an salt with an sodium, and with that also it liberates an CO2. So these are the two observations one should observe. And whenever again it is been treated with an HCl, so it will reprecipitate. So here what happens, the sodium chloride, it has been formed, and this sodium chloride, it is more soluble in water compared to an benzoic acid. So this salt, sodium chloride, it gets solubilized in the water. The same reaction, or in the same test tube, this reaction, it has been proceeded. So whatever the water molecule, it has been formed in the second step, The fact that it is used for an urinary tract infection, because benzoic acids are easily solubilized in the urinary tract, as urinary tract hydrate, it forms an benzyl alcohol. Addition of an soda lime, that is calcium oxide and NaOH, it forms an benzene plus calcium carbonate. We have seen some qualitative tests. So first test we seen, that is litmus acid test. After that, bicarbonate test. So in case of litmus acid, blue turns to red. In bicarbonate CO2 it has been evolved, and again HCl it is added. It forms an again in benzoic acid. After that, ester fragrance, that is formation of an ester, and it gives a smell of an ester. And we have seen some uses about that, representative uses like germicide in case of a urinary tract infection, preservative some for some